Hello. So today we're going to be looking at annihilation. Annihilation is what happens when matter and antimatter meet. And in order to do this, we're going to think about probably the most famous equation. And that is, obviously, E equals mc squared. It's telling us something about the amount of energy that's available to us if we can access it in matter. And really what we've got here, we've got the energy is equal to the mass in kilograms multiplied by the speed of light squared. That's obviously going to be an enormous number. And we're going to look at the sort of implications of this a little bit later on. Now, I'm sure you know this, but this equation comes from Einstein. And what Einstein said was that mass and energy are equivalent. They're basically the same thing. It's a bit of a strange concept, though, but you have met it before. You've probably met it lower down in the school. If you think about something like the sun, and this is a dramatic oversimplification, but have you ever thought about where the actual energy comes from in the sun? We know that there's a process of fusion taking place, which is basically small nuclei joining together to form larger nuclei, but that's just like gluing things together. Where does the actual energy come from? And it comes from something like this. In this picture here, I've got 2 protons and 2 neutrons. And if you weighed them, they would have a certain amount of mass. Now, when they fuse together to become a helium nucleus, the mass of the helium nucleus here is going to be less than the mass of the individual particles. We call this a mass deficit. And that bit of mass that goes missing is actually turned into energy. And if you can work out in kilograms how much mass goes missing, the equation E equals mc squared is going to tell you how much energy has actually been released. Now, in the start of the video, I said that this was going to be about annihilation. So where does that come in? And really, this is looking at sort of what happens when antimatter and matter meet. And I guess the question, first of all, is where is all of the antimatter? There's no real reason why the universe around us, or none that we know of at the moment, why everything is made of matter. There's not really much antimatter around. And that's a different question. What this is about really is if we make antimatter, and we can, it happens in cosmic rays. When they decay, we get antimatter. You can make antimatter in particle accelerators. But it doesn't stick around for very long at all. And the reason for that is that any time an antimatter particle meets its matter equivalent, so like in this picture here, we've got an electron meeting a positron, they will annihilate, they will stop existing, and they will turn to energy. And the amount of energy that you get from E equals mc squared. So the sort of thing that would happen is, and I'm going to apologize for the diagram here, is we've got an electron and a positron colliding with each other. And when we say that it annihilates and it stops existing, it means that it changes to energy, but what's the form of that energy? And what we really mean is that it produces photons. And photons, particles of light, massless particles, really a packet of energy, I think we described it as last year. Now, I would like you to have a think about why this picture is sort of so poor. I've said it's a poor diagram on there. We've got an electron coming in from the left, it's coming along this way. We've got a positron coming in from this way. They meet, and we have 2 photons emitted. Now, the problem I've got with this is the direction that these photons would be going. There's no real reason for them to go off at different angles like this. In fact, that's wrong. We'll look at why that is in a second. But let's look at this as an equation. So this is the equation that you get, and this is using sort of nuclear notation. If you were to just sketch this out in your notes, you'd probably just say electron plus positron, then arrow, and 2 gamma particles. Two photons, sorry. So why have we got the zeros and ones here? So we've included the mass number and the atomic number of each of those particles. And obviously the mass is effectively 0. It's not 0, it's just much smaller than the atomic mass unit or the mass of a proton. The photon over here, no mass and no charge, which is why it's 0, 0. Now, the thing that I found a little bit odd when I first met this is, why does it produce 2 photons? And that comes from our conservation rules. Because if we look at this equation, I'll put up the next little slide. Okay. Charge was conserved. So if we go back here, we've got a negative charge and a positive charge on the left-hand side. And on the right-hand side, no charge. So it's conserved. We haven't got mass being conserved, and we haven't got energy being conserved, but we have got mass energy being conserved. So that's all right. But we also have to obey conservation of momentum. And in this case here, if these 2 electrons come in from opposite directions, so that the total momentum is 0, they annihilate with each other. The things that are produced afterwards have to have 0 momentum. Now, you can't have that with 1 photon being emitted. If 1 photon goes off to the right, another photon has to go off to the left. So there has to be 2 photons produced. So what Einstein's actually told us is that if we've got energy, it can change to matter or mass. And if we've got matter, it can change to energy. And in the right some circumstances, it can change between those things. And that's what happens in particle decays. And also that's the whole point of these particle accelerators that we've talked about, or we've mentioned briefly anyway, things like CERN and the Large Hadron Collider. Because the idea behind these accelerators is to find or to make new particles. And the new particles that we're trying to create have got more mass than the things that you're trying to create them from. So how does that work? And really the idea is sort of something like this. In the Large Hadron Collider, they accelerate protons and antiprotons in opposite directions in a circle and get them going really, really fast. Now, when they collide with each other, they annihilate. So if we look at what I've got written up here, where's my finger gone? There it is. We've got the mass of the proton and the mass of the antiproton. And we could annihilate those, and the energy that's produced would be enough energy to make something twice the mass of a single proton. But we make them go really fast, so they also have kinetic energy as well. So the new particle that's created can have a mass that's equal to the mass of the proton plus the mass of the antiproton plus the energy from the kinetic energy of the proton and antiproton can also turn to mass. So you can end up making something that's many, many, many times greater in mass than the mass of your initial particles. We'll talk about this more when we come on to particle accelerators. So the final thing we can talk about is the opposite process. So far we've talked about starting with matter and antimatter, and they collide with each other and they annihilate, producing photons. Now, those photons, if they've got enough energy and in certain circumstances, often if they interact with the nucleus of another particle or sort of collide with something, they can go on to produce new particles themselves. And this process, or the most common one of these processes, is called pair production. Now, pair production is where you have an energetic photon, like this one coming in from the top left, and that will decay into a pair of electrons and positrons. And that's going to conserve all our laws that we've talked about. So lepton numbers conserved, because obviously the photon isn't a lepton, so it has a lepton number of 0. And we've got the electron and the positron, each of those with a +1 and -1 lepton number, so 0 after the interaction occurs. Same with charge. You can see that's conserved. And actually, the electron and positron will go off at an angle from each other because momentum will be conserved in 2 dimensions. This is a little bit weird to think about, but if you think about the photon coming in from the top left, that already has momentum. So momentum, the particles that produce will have momentum in that direction. But if they're going to spread apart from each other, which they do, otherwise they would annihilate immediately, which would happen sometimes, they're going to go off with equal momentum at right angles to that initial direction as well. There's a bit more about this that I'll talk about in another video, where we'll talk about how we can actually calculate the masses and energies of these things. And obviously you might be interested in sort of what photons could produce an electron and positron, or equivalent question is, if I annihilate an electron and a positron, I think I said proton a minute ago, if I annihilate an electron and a positron, what will the energy of that photon be? And if you know the energy of the photon, you should be able to work out the color of that photon. So we'll be doing that next. So thank you very much.